I don't know why I accepted this talk, because many other people here might be better than me for doing this overview. I will try only to remind that inverse problem theory is probably the most important theory developed in seismology, because it has many applications, not only in seismology, but also in science in general, and of course many applications in other fields of earth science and physics. And so it's important to see that, to my sense, inverse problem theory is a very important field, and it's very difficult to summarize the different development during the last 50 years, because they have been so numerous. And what I would like to do is very simple introduction, starting from almost from scratch, and to show the different concepts which might be useful for other talks during this short course and workshop, and for practicals for students, that it might be useful to have a common language. And I guess the language I try to use is quite common for all people. Okay, and in this framework of inverse problem theory, we can say that Albert Tarantola was really a leader for several decades, and he tried to promote a new approach in inverse problem theory, the probabilistic approach, and which finally becomes a Bayesian inference. And in that respect, okay, does it work? Yeah. In that respect, from a personal point of view, Albert Tarantola, his initial means many things. As I told you, I did a lot of work on anisotropy, and also some work on anelasticity, anelastic tomography, and finally, I will rapidly discuss about adjoint tomography. So you see that. But it is clear that Albert was a pioneer in the probabilistic approach in the Bayesian inference, but he also did some interesting work on neural network in the 90s, and also he did a lot of work on full waveform inversion. Okay, so first of all, what is an inverse problem? It's not so easy to define. I tried to find a definition not too complicated, but it's the process of calculating causal model parameters, M, from observational data, D, that produce them. The inverse of the forward problem, it is the inverse of the forward problem, starting with the causes or processes and then calculating the effects. Usually, but it's not always the case, the forward problem is associated with a theory, but it's not, it can be explicit or implicit. Most of the time this theory is coming from physics, but not necessarily. And what we can say is, from a general point of view, we can define, is it working? Is it a pointer somewhere? No? Okay. We can define the functional, it can be a function, a matrix, or any kind of mathematical operator, which can relate the data and the model parameters. And this is usually written in this simple way, D equal to G of M. And so we have two spaces. I put them, they are disconnected, but they can have some overlap. And so we have the model space, data space, and it is what we usually use in the inverse problem theory. The forward problem will relate the model space to the data space, and the inverse problem, we try to get an estimate of the model space parameter by the inverse problem by trying to invert the operator G, the functional G. Okay, so we have different kind of difficulties in inverse problems. We have, of course, what looks the simplest one. It is a linear problem, but it's what we have some the best solutions. We have slightly. Oh, it's interesting. Come back home. Okay. So that's the linear relationship. We have slightly nonlinear problem where we are not exactly. We have a simple variation of data with parameters, but it's not linear, but it's quasi-linear, and we can apply classical techniques of first-order perturbation theory, for example, and we start from a starting model. It might be the a priori model M0, from which we can calculate synthetic data, D0, and we apply a whole mathematical tool inversion where we calculate the sensitivity kernels, and by inverting the sensitivity kernels we can solve the inverse problem. The most difficult inverse problem is when you have a nonlinear problems, and nonlinear problems, you see you have a very complicated variation of data with parameter, and we have some schema, and we have a complex variation. In that case, it's necessary to use more statistical and probabilistic approach, and we have to explore parameter space, which is not so easy, and some strategies must be defined to be able to explore the whole space. Okay, so let's go back to the linear problem. In the linear, we have a linear relationship between the data and the model parameter, but the main problem is that this matrix usually, or this it can be a linear function as well, is not a square matrix. If we consider a matrix, we have usually the number of data, ND, is different from the number of parameters, NM. In the best case, we have much more data than model parameter, but it's not always. We have either an overdetermined problem or an underdetermined problem. So it's not a square matrix. And the simplest way to solve the problem, I guess you know, solution by multiplying by the transpose of the G matrix. And we can find, it can be shown that it corresponds to the least square solutions. So the GTG is a square matrix which can be inverted, and so we can find the model by this expression where we have the GTG minus 1 inversion. And by the way, it's interesting, some people know that, but when Albert was in IPG, his group was named GTG, which means a group of what does it mean? Tomography group? Yes, geophysical tomography group, GTG. Okay. So this matrix, of course, can be huge or can be small, but you have a lot of data or a lot of parameters, and I will go back to this point. It can be a huge matrix and not so easy to invert. Okay, now when we have a slightly nonlinear problem, as I told you, we have classical techniques, I don't want to detail, which are basically related to first-order perturbation theory. And the literature exploded in the 70s, and we have a very seminal paper. I advise you to read these old papers. I know that before 2000, you don't like to look at old papers, but these papers are really important. In particular, the Backus and Gilbert, the paper by Franklin, Jackson, Wiggins, and so on. And so it's very similar. We have good algorithms to iterate and to solve this slightly nonlinear problem. So it's not so different from the linear problems. Okay. Okay, so what did I want to say? Yeah, okay. So when we have solved, so far we didn't do a lot of hypotheses on the data space and parameter space, but we have to wonder if we do this inversion, GTG minus 1 GT, do we find a good fit of the data? So we have to ask the question of the quality of the fit, and we have to make some estimate of the quality of the fit. And in that case, we have to introduce what is named the cost function, and it can have different names, can be called as well the objective function. And the idea is to see when we calculate the residuals between data and the model, I call that epsilon I, we have to minimize the sum of all these residuals to get the best fit. And when we do that, we have to introduce norms, and there are two popular norms, the L1 norm, where we only calculate the sum of the absolute value of residuals, and which is probably the most used is the L2 norm, which is a quadratic norm. Take the square of the difference between data and synthetic. Okay, I would like to mention that the reason why we use usually the L2 norm, it is because of probabilistic reason, because Gaussian distribution of errors. But sometimes it's not very robust because it's very sensitive to outliers. If you have some outliers in your data, it will have a strong influence on the cost function. Okay, so now we did not discuss about the uncertainties, and we have uncertainties on data. Later on, we'll discuss uncertainties on model parameters. I guess Alison will different points, but it's important. You know, so far we did not do a lot of hypotheses about your data and your model space, and now we have to take account of the uncertainties on data and on model. Okay, so a simple way to take account of uncertainties and error bars is to weight the residual by the inverse of the error bar. It is named sigma, and it can be done on both cases of norms. And it's easy to understand that if you divide by the error bars, when you have a very large error bars, the weight of this measurement will be small, but if you have a very small error bar, 1 over sigma or sigma square will be large, so you give more weight to good data. Okay, and so when we start to discuss errors, we have to discuss, and uncertainties, we have to discuss probability distributions and a Bayesian approach. And again, I don't want to detail this Bayesian approach since we have several lectures on this topic and by Andreas and Klaus Mosgaard, and but again, it was introduced by Albert Tarantola, but also by people in US, Jackson and Matsuura, and so on. Okay, so okay, so what I forgot. No, okay. So now we have the model space, the data space, and we have to weight by taking account of the uncertainties. And to generalize the errors, we introduce what we call a data covariance function, CD, and it's very easy. You know, what we did is that when we transform this expression by using transpose of the residual, multiply by the covariance function, and again multiply by the residual. So it's very easy to take account and to calculate this cost function by taking account in the data space data covariance function. As I told you, the issue of data uncertainties is very, very difficult because you have different ways to estimate the uncertainties. You can take account of the quality of the instrument. You can take account of the fact that you have varying conditions when you do the experiments, and so you introduce a lot of data errors, and so it's a difficult issue to measure or to estimate the uncertainties on data. Okay, and so what is the most common when you do a lot of experiments is to have a Gaussian distribution of errors, and when you have a Gaussian distribution of errors, it is shown here, you have to introduce in the cost function. It is easier to use the L2 norm for in the framework of the probabilistic distribution. Okay, and so I don't want what. Okay, so we have this Gaussian distribution, and when we use that, we can derive very easily the best estimate, again, by taking account of this covariance function of data. And again, I don't want to detail, but for a slightly nonlinear problem, you can do basically about the same equations, but you have to make some iterations to converge. Okay, so an important point is that so far we only discussed the data space, but not the parameter space. And I think that probably it is an important contribution in the 80s of Albert Tarantola and others is to make the equivalence between the data space and the model, and to take account of the a priori information that you have on your model space. And it's important because when you use a least square solution, very often you have a lot of instabilities, and you need to regularize your solution and to smooth sometimes the solution to avoid a lot of in the inversion. And at this stage, the simplest way, the simple way to do it is to add to the cost function a second term which has exactly the same structure as for the of the first term related to the data space, and we introduce a covariance function of parameters, and we introduce the difference between the a priori model and the model we are looking for, which is supposed to be the best model. Okay, so that's very important to introduce this equivalence between the data space and the model space. And that's to illustrate this figure. We have for the data Gaussian distribution. For the parameter, model parameter, we also have the Gaussian distribution, and we try to find the best solution, and you see that you have to combine both kinds of information on the data and on the model parameters. Okay, so to go back, now we have these two spaces, data space, model space. In both space, we have defined covariance functions, one for data, one for model parameters. And in regularization, we have to find the minimum of the cost function. Sometimes it is named as well the chi-square, it depends. Okay, you have different notations, and you have to calculate the minimum of the cost function by deriving. It is basically true only for for linear, quasi-linear problem. Okay, so in the 80s and 90s, Albert defined what is called the generalized inverse problem, and he used, okay, I will only show the example of Gaussian statistics for the least criterion, and he introduced the Bayesian approach to solve the problem. And in that case, it's quite easy. In the data space, if the measurements of Gaussian distribution, you can calculate the probability distribution of data, which is related to the exponential of this part of the cost function, the residual CD minus 1 residuals. So it is this kind of probability distribution. In the data space, we can do the same. If we have a Gaussian distribution, we have again this a priori distribution of model parameters. And finally, what we can, okay, it is what I showed previously. And if we apply now the Bayes theorem, which will be detailed, of course, the most general presentation of the Bayes theorem, you can see that the a posteriori distribution of probability for the model parameter is given by the product between the a priori probability distribution model and the probability distribution on the data. And in that case, you easily see that you obtain something which is the exponential of the cost function. And so you see that we can relate, we can find the solution by maximizing this probability or by minimizing the cost function, which is here. Okay, so you see it's a very simple approach, and it will be detailed in several lectures this week. Okay, and so yeah, it is not different. So we have to derive the algorithm. It is for simplest case, ds over dm equal to 0. And to illustrate this part, I show this figure of Malcolm Sambridge, where you have the that is a Bayes theorem, where you have the prior probability distribution function, the likelihood function, which is related to this part of the probability, and the posterior is the product of both, and you find the posterior probability distribution function. Okay, so now I will rapidly address the issue of nonlinear inverse problem. As I told you, it's very difficult because you have a lot of minima, and so you cannot apply the perturbation theory. For example, it will not work close to the solution, which is usually not the case. And so during the 60s, so you were not born, and there were a lot of attention regarding the Monte Carlo approach, I guess a way to explore the model space. There was the algorithm of Metropolis developed in the 50s, which was applied by first in Russia by Kelly Borok and Yanovskaya, by Frank Fretz in US, and later on this kind of Monte Carlo approach was followed by, for example, by Klaus Mosgaard and Albert. And there are many different strategies. It's very difficult because the parameter space might be huge, of course, it can be infinite. And so you have to define many different ways to explore where the probability distribution is the largest or significant. And so there are many different ways to do it. We can using Markov chain, Monte Carlo inversion, and there are a lot of different techniques. And this week, I only mentioned some of them: neural network, simulating annealing, neighborhood algorithm, and so on. And Léonard Seydoux and Thomas Baudin probably will develop this part of complicated solving of nonlinear problems. Okay, so I would like to show that the algorithm of Tarantola and Valette, which was published in '82, has this kind of complicated formulation, but it's very easy to implement. And I remember that I was a student, and I to Albert was saying, okay, you have to use my inverse problem theory because it is the best, and so on. And I did that. It was my first paper, actually. I calculated, okay, we can also calculate the a posteriori covariance function, the resolution for quasi-linear problems. And I say, oh, yeah, but we cannot invert the complex waveform. At that time, it was too complicated. That's an example of earthquake data. But we can invert very easily. We had the computational power to solve problems with not too many independent parameters. And I did that by using secondary observables, which are phase velocities or group velocities, or for body waves, travel times. And in that, the inverse problem is tractable. And I was very proud to publish my first paper about the 1D model of S-wave velocity by inverting, using the algorithm of Tarantola and Valette, the S-wave model. Okay. Okay, and so to go back. So we defined different concepts here: data space, parameter space, forward problem, slightly nonlinear problems. We can introduce errors on data, a priori errors on parameters. And for Albert, at that time, he found that travel times, phase data were too simple. And he wanted to implement the full waveform calculation, and he was at the base of what is now the spectral element method. And he also wanted to apply this forward calculation to inversion of huge data sets. And so he was very active and proactive for buying big computers. And of course, from the theoretical point of view, he said, okay, forget the isotropic elastic medium, you have to move to anisotropic and anelastic medium. Anyway, but big computers. He was promoting to use big computers, and his basic idea is think big and general and ambitious. And for example, he showed this example that he didn't like small and slow vehicles, I guess but he always preferred this kind of fast and elegant Ford Mustang vehicle, and he tried to apply his philosophy to big computer, and he managed to buy the first parallel computer in France, which was named the Connection Machine, and it was a very beautiful computer, a lot of lights, it was very impressive. And he understood that if we want to go forward for inverse problem, we need a lot of computer facilities and powerful computers. Okay, so now I will try to go back to what I said and to go back to the different point of the tomographic imaging. And I will say that tomographic imaging is like a French cooking recipe. You have a lot of ingredients, and if you want a good dish, all ingredients are important and must be carefully chosen, and you need very good quality. Okay, for example, the first point I did not discuss is the theory. The theory is always imperfect, and what should be great should be able to define the error on the theory, which is almost impossible. But from the theoretical point of view, if you are able to do that, it will add to the covariance function of data. But it's a difficult task to estimate the error in the theory. Now I will go back to data space. That's also, for me, it's very important, because most discoveries in earth science arise from seismic data. So if you want to make new discoveries, you need high quality seismic data. And we are lucky in seismology because we have many kinds of data. We have, of course, at long period, we can derive from this long record free oscillations. We can use surface waves, of course. And I'm biased because I work basically on the regional and global scale. We can use surface waves, and of course, we can use body waves. And you see, we have a lot of seismic data, and it's important because we have to collect as much data as possible to have a better image. Okay, and more recently, we are able to use ambient noise, and for example, in at periods shorter than 30 seconds, we have, of course, usually people are using only the ballistic waves, which are the waves originating from earthquakes, but we have a lot of records, which is before the arrival of seismic waves, we have noise, and after we have the coda waves, and I guess many people here are working on this kind of. There is also at long period the seismic hum. Seismic hum was observed by the Japanese at the beginning of the 2000, where they observed that when you have no earthquake, you can observe free oscillation of the Earth, and you can measure the eigenfrequencies. At long period, it can be useful because you can make global tomography of the Earth by using this long period noise. And we were expecting that it might be useful for the Mars exploration, because on Mars you have very few Mars expecting to detect the free oscillations of planet Mars, but actually so far, well, it's not so to extract free oscillation of planet Mars. But that's another kind of application. And of course, you know many applications for the microseismic noise, for doing local tomography, for doing monitoring of physical processes and so on. So I don't want to detail this point, but that's important. Okay, so to go back to Albert, in the end of the 80s and the 90s, IPGP was developing the broadband network of geoscope, very broadband seismometers, excellent quality, but he was with that because he wanted big networks. And so he tried to promote networks with hierarchical multi-scales and global scale, regional scale, and local scale. And he said, yes, we have to do that because the structure of the Earth is multi-scale by essence, so we really need big networks. And actually, there were during that time many initiatives. The best, probably the most popular, was the US array, where you have this kind of regional scale broadband network. And on the seafloor, I show an example. We have now, we are able to do now on a routine basis ocean bottom experiments. And I show here that French-German experiment, Rom-Rom, around La Réunion Island here. You can see the Central Indian Ridge, Southwest Indian Ridge, Madagascar, and we were able to install more than 60 stations, OBS stations. And so you see that the move toward more and more dense networks is going on, and we can expect that new discoveries can be done by this approach towards a multi-scale approach. Okay. Of course, he didn't know that we are starting to explore other planets, and there was a famous InSight experiment in 2018 where it was possible to install very broadband seismometers on planet Mars. Okay, another point which is important in the sense that data are the most important, we also need new instrumentation, new instruments, because new instruments means a new way of looking at physical processes. And of course, during the last workshop, you had some classes about rotational seismometer, classes on DAS, distributed acoustic sensing, and what I would like to promote is the development of torsion bars for measuring prone gravity seismic signal, but I will discuss that next week. Okay, so theory, data space, and now how can we choose the model parameter space? It's not, again, it's a difficult issue because we have a lot of possibilities. You can say, okay, my function will be described by pixels, which correspond to a local basis function, or we can try to use more Gaussian covariance function, which is a way to take account of the probabilistic approach that we are using in this problem. And the Gaussian covariance function, we have two parameters. We have L core and sigma m, and they have two different functions. The correlation lengths help the smoothing of the model. If you have a very large correlation length, you will have a very smooth model. If you have a very small correlation length, you will have a very heterogeneous and small scale model. And sigma m is more the damping, because if you have a very large sigma m, you will make very large space available for. So both have a clear physical meaning. At the global scale, usually we prefer to use spherical harmonics because they are global basis function, and so we can expand any scalar function on this basis of function. Okay, so when you try to define your model parameter, you always have to wonder what is the minimum number of parameters needed to explain the data. It is a principle of parsimony, and so it is what's named the Occam's razor. And so that's important to understand that the number of parameters can increase very rapidly. For example, we have two kinds of physical parameters. We have the physical parameters. For example, we have the density plus the 21 elastic parameters of the elastic tensor. But we have the geometrical or geographical parameterization, which will give you the lateral resolution. And I always show this example that even for a not so good tomographic model at the global scale, if you want a lateral resolution of 1,000 kilometers, a radial resolution of 50 kilometers, if you introduce your 22 physical parameters, you must retrieve more than 600,000 parameters, which is not so easy. So you understand that the inversion of so many parameters is by itself a difficult challenge. Okay, and so that's to summarize what I said, different kind of seismic data, different kind of model parameterization, and we have to wonder how to go forward. For many decades, people were using secondary observable, eigenfrequencies, travel times, dispersion velocities, and so of course we have to move toward full waveform inversion. Again, in terms of the forward problem, for many years people were using ray theory, but more and more often now we are able to calculate synthetic seismograms in a heterogeneous medium by a spectral element method, for example. And of course, another point is we have to move from isotropic medium to anisotropic and anelastic medium, because in essence, anisotropic and anelastic. Okay, and so to go back, I will not detail, but Albert was promoting the calculation by numerical techniques, and he also develops the inversion by adjoint tomography. I have to, well, okay. And so the idea is very simple. That's the example of the algorithm he developed, and you can isolate of the algorithm where you have to invert this huge matrix. This huge matrix, I call that W, is not exactly the Hessian, because the Hessian mathematical definition is slightly different, but basically it is the first order Hessian, and this matrix can be huge and very difficult to invert. And so people who promote the adjoint tomography or transpose tomography propose to approximate this W operator by something proportional to the identity operator. By the way, it's an excellent idea, but very difficult to implement, because if you neglect the Hessian, sometimes convergence is not so easy, so it's not so easy. Another point I would like to address is when you do waveform inversion, you have two ways to do it. You can work, okay, maybe. You can work and measure the difference of travel time between different phases, or you can work directly in the time domain on the amplitude. And in that case, you can either invert delta t or delta e or both, but it makes a big difference. For example, if your starting model is very far from the data, which can happen very often, A, which is the difference in amplitude, might be larger than the signal by itself. So very difficult to implement. So it's the reason why when you do full waveform inversion, the best strategy is to first fit the phase. So to be able to have the synthetic and data very close in phase, and in the second step, you can invert for the residual in amplitude for retrieving attenuation or focusing effect and so on. Okay, so that's a point I wanted to detail. I wanted to show, because it's a recent result we get recently, by using full waveform inversion by my students, Mathurin Wamba. He came many times to several workshops, ITN workshop. And what we did, we used the OBS data in La Réunion Island, and also other permanent stations all around. And we derived, by using joint inversion of surface wave, body waves, area modes, we derived a tomographic model below some hotspot in the Indian Ocean, from the surface down to the core mantle boundary at 2,900 kilometers. And we are very surprised because, of course, we see vertical conduit, but not necessarily just beneath a hotspot. And we have this strange zone between 660 and 1,000 kilometers, where we have low velocity. It is a stagnant ponding zone beneath plumes. And in the second step, you have other conduits going from this extended transition zone up to the surface. So, you know, it was very surprising because we are able to retrieve these tomographic images because we have a very dense network in the Indian Ocean, and we use all seismic data available all around. It was not possible, and we were able to have a tomographic image with a good resolution. That's an image where you see these two zones at the core mantle boundary here and the stagnant ponding zone in the extended subduction zone. Okay, and so that's an interpretation. So with volcanic plumes, and you know, people believe that there is no more discovery to be done in the deep Earth. I guess it is not true. We still have to understand better how it works, and these ponding zones were only recent discoveries. Okay, I have 2 minutes. Okay, I will not detail. I have to conclude. Okay, the last point, I had many discussions with Albert, was about adjoint tomography and time reversal. Actually, at that time, I was working on the time reversal of seismic waves to locate earthquake and to investigate earthquakes, and we realized very rapidly that there are many similarities between this kind of approach. Okay, now I call that time reversal, but it's now more popular in terms of back propagation technique. And we realize, okay, it's a paper I don't want to detail with Hitoshikawa Katsu, that when we do time reversal imaging, we also do this approximation of the Hessian proportional to identity. And so if we have a good Green's function, we can retrieve the force associated with the earthquake. And from the physical point of view, it's easy to understand that when you do adjoint tomography, you need two seismic wave fields, one which is the direct wave field, the second one is the time reversed. It is related to the adjoint operator. We time reverse the residual wave field, and we correlate both time reverse wave field and downgoing wave field, and we explore the parameter space, and we find where are located the different anomalies. So it's interesting. Yeah, from a physical point of view, we have some consistent approach between time reversal and adjoint tomography. Okay, for Albert, we need millions of stations and millions of receivers. Anyway, but the principle is the same. Okay, I will conclude. Okay, so to conclude, of course, Albert was not the only one working on inverse problem theory, but he was a strong promoter of science, and he was always open-minded, provocative, but always generous. And he said that you have to address scientific issue always in a very general way, and don't try to limit your ambition. Be ambitious. He always say that money is not an issue. It's not completely true, but he said that we can always find money. There is a lot of money everywhere, and so money is not an issue. We need big computers. We need very multi-scale networks, and we have to go beyond the consensus. Okay, and so Albert was really a brainstorm, and I hope that this workshop will be a good opportunity to have some good brainstorming sessions. Okay, thank you for your attention.